So honestly, I was pretty nervous. We were running a really challenging experiment to explore the limits of today's quantum computers and how they compare to classical computing methods.
I try not to view this as a competition between classical and quantum computing, but I did go into this experiment expecting the supercomputer to outperform the quantum computer. So my involvement in the project was to help simulate this quantum experiment on some of the largest and most powerful supercomputers in the United States, including at the Berkeley National Lab and the National Energy Research Scientific Computing Center.
We wanted our collaborators at UC Berkeley to use classical simulation methods to verify whether our noisy quantum processor was producing reliable results. We also wanted to push our device to limits where their methods might struggle. We didn't want them to come back to us too soon and say, yeah, we solved the problem very easily.
But using some of the novel error mitigation techniques that IBM has introduced, we actually found that the quantum device easily matched exact classical results and outperformed approximate classical results in cases where the exact answer was available. Impressively, even as we moved to circuits beyond exact classical methods, quantum still appeared to be more reliable than some of the approximate methods that we tried on these large supercomputers.
For quantum hardware, scale and noise have always been the biggest problem.
On scale, IBM's made more progress than anyone else, but noise is a different problem altogether. Quantum computers are very sensitive to noise, disturbances that cause errors in their computations. IBM has spent years developing methods for filtering the effects of noise out of quantum computations. This is called error mitigation. We were only able to do this because we've now built a quantum system of unprecedented scale and quality and developed the ability to manipulate noise on a quantum system at the scale.
Having good, reliable 127 qubit devices with high coherence times was really a prerequisite. The hardware really enabled this project to happen.
We wanted to see if error mitigation would allow the quantum computer to even keep up with the accuracy of a classical supercomputer at this scale. With the error mitigation techniques used in this paper, we run our calculations and slowly turn up the noise. Then we extrapolate back to the zero noise solution.
How do we control and manipulate hardware at this scale is quite unprecedented. The answer to this question did not exist before.
Understanding the root cause of these discrepancies will allow us to improve both methods and is an example of the benefit of the interplay between quantum and classical. Together, we can realize a device that can solve interesting problems.
As we increase our number of qubits, reduce our error rates, and improve on these techniques, we will see a growing collection of problems where quantum computers can provide value.
Eventually, we'll reach a point where we can truly learn something new from quantum computation that we weren't able to access through classical alone. A point where we can really push at the boundaries of human knowledge.